What is our today's topic? If I give you the question, what do you mean by candidate key in database management system? So here our topic of discussion is key or candidate key in database management system. But what we are going to learn today, because there are some associated rules too. So first, just think of it. Whenever I am talking about database management system, means I am talking about repository of data, storage of data, and how this data will be stored. It is dependent on what kind of database management we are using. Since we are using relational database management system, the meaning of this relational database management system is whatever information you have to keep it in a particular table where the columns are known as attributes and the rows are known as tuples. This is the very basic thing that you have to remember in each and every class. So now here what is our topic of discussion. So whenever I am talking about any particular table in a relational database management system, this table will have some specific attribute. Say the table is having attribute like student roll number, student name, student address, like this. And here keeping data inside the table means we have to fill up some student information with some specific value, say Kolkata, Delhi, like this. Now what is the problem? So whenever we are defining any particular table, the first concept that you have to understand, what is the key of this table? So what do you mean by key? See, key means a attribute or a set of attribute. Means you can take one single attribute or you can take combination of any number of attribute, it doesn't matter. But what is the role of a key? Role of a key means if you know some of the information about this key, say roll number is 1 and AA. So the responsibility of this key is it will identify one specific tuple, means it will try to identify a particular tuple in the entire table. This is the main purpose of this key. So now if you are not able to identify a proper key for your database table, the problem is it will not give you a unique tuple as an output. So identifying a unique tuple in a particular table is very important. So whenever I'm talking about roll number 1 and the name of the student is AA, then it should represent only one particular student, not more than that. And also, according to my definition, a key means it is a collection of attributes. Means in this case, if I keep only student roll number as a key, then if I know the roll number, then it will easily identify one specific student. But here the question is, who will decide how many attributes should be there? Or how should I understand that how to create those keys? Because in real life the problem is whenever a particular table is given to you, it will have large number of attributes and large number of information. Finding appropriate key is very difficult for us. So now today we will learn one mathematics by which we can easily find out the key. More precisely, today I will talk about candidate key. In general, we have three kinds of keys: super key, candidate key, and primary key. Apart from them, we have other keys too that I will discuss. But finding candidate key is the most difficult task in database management system. And now you have to understand the first question, why we need to find the candidate key, why it is important. So whenever you have particular information stored in the database management system in the form of a table, the first problem is how many numbers of attributes should be there in the table, we don't know. So we have to find it out. Means our target is to keep this table simple, and this table should contain less number of attributes. So this is our target. So in one word, what is our objective? Our objective is to normalize the table. Normalize the table means we will keep minimal number of attributes in the table, so that on this table we can write good SQL query to fetch some information. So this is our target. So whenever we have our database management system where all the information are stored in the form of a table, and finding normalized version of this table is very important. Now the question is, who will help us to find this normalized table? This candidate key. Once you have identified the candidate key of your table, then it will be very easy for you to find out the normalized version of this table. That's why finding candidate key in this session is very important. But how could we find the candidate key? It will come with some sequence of steps. It is not a one-step approach. Now, let's start with the concept. So, our objective is to find the candidate key and also find out what are the properties associated with the candidate key. But we are not coming into this portion directly. So before that, we have to follow two steps. First, we have to understand what do you mean by Armstrong's axiom. After understanding Armstrong's axiom, then I will go for the next step, which is known as finding closure. And then only we can move on to the concept of finding candidate key. So I think now it is clear to you what we are going to do. So we have to learn the axiom first, then we will learn the closure, then only we can find the candidate key. That's it. So now let's start the class. So now the first step is we have to learn what do you mean by Armstrong's axiom. So why we are learning it? See, try to understand this. Armstrong's axioms will act like a constraint that will help us to work easily on the database, or you can say that these axioms will use to infer some functional dependency on the relational database. Functional dependency that I was talking yesterday. But try to understand first the rules. So what are the available rules? So whenever we are talking about Armstrong's axioms, then you have to understand we have two specific rules. First one is known as primary rules and the second one is known as secondary rules. So now first we have to understand what are these primary rules. In case of primary rules, we know that the first rule is known as reflexivity. The second rule is known as augmentation. And the third rule is known as transitivity. So these are the first three rules. And the second rules are union, decomposition, and pseudo transitivity. Now, I am not going to define each and every rule. I will define you one shortcut trick by which you can cleverly use these rules with a very little concept. Means try to understand here why we are learning this Armstrong's axiom, so that we could find out the concept of closure. And why we are finding this concept of closure? So that we could find the appropriate candidate key. And why this finding candidate key is important? So that we could create a very good database table. And very good database table will help us to write the good SQL queries that will help us to fetch proper output from the table. So this is the concept. Now, first I will discuss this closure part, means how to use all these rules of Armstrong's axiom to find out the closure. So now let's begin with the shortcut trick. So here say it is given that there is one relational table. So whenever I'm talking about R, always you have to understand R means the entire table that I am talking about. Then if I write something within first bracket, then you have to understand that these are the attributes. Attribute means names of the columns, that is student roll number, student name, something like this. So here I am denoting with A B C D E F G, means no specific name is given to the attribute. And say here some functional dependencies are also given. So name of the table is given, attribute information is given, and some functional dependencies are given. So here I am giving you one short recap. What is this functional dependency? The meaning of functional dependency is A arrow BC, means if I know the value of attribute A, then I can search the value of attribute B and C. That is, if I know the student roll number, then I can search for its name, and also I can search for its address. So this is the meaning of functional dependency. Similarly, BC arrow DE means if I know the value of B and C attribute, then I can search for the attribute D and E. This is the concept. So this is given problem. So we have the table attribute information and we have some set of functional dependency. Now what is our objective? We have to find out closure. So the first point is, whenever a functional dependencies are given to you, look at this left hand side. Means calculating closure is done only on the left hand side. So how you can represent? So in the left hand side we have A. Closure of A means A plus. Then closure of BC plus, closure of D plus, closure of CF plus. So here my point is, whenever you are going to calculate some closure, the first thing is some dependencies related to this table should be provided to you. Those are known as functional dependencies. And closure can be calculated on the left hand side only. And right hand side component you have to find out. Now why we are finding closure, I have explained. But here try to understand, at the beginning of the class, I have clearly stated that for finding closure, we need to take the help of Armstrong's axioms. But learning and remembering all those axioms are not possible. So we will learn some shortcut trick by which we could use those axioms to find out the closure. Now the second question is, why we are fighting for this closure? Because I want to find out the key attribute of a table. Maybe it is a super key, maybe it is a candidate key. And I have explained that finding candidate key is very much difficult. So today I will focus on this. So if I find out candidate key, then super key will be automatically identified. So this is my starting point. This is my ending point. And now I am at the middle. Now first try to understand how to find out the closure. So whenever you are at this point, now you have to find out the RHS. What you will do? The first thing is, we will use the concept of reflexivity in the Armstrong's axiom. So what do you mean by reflexivity? It is very simple. Whenever something is given to the left hand side, just copy this into the right hand side. Means if I know the value of A, then I can easily find out the value of A. Means if I know name of the student, so name of the student is known to me. It is a very trivial thing, means it's a very silly thing. It is also known as trivial dependency. Means if I tell you that what is your name, you are stating me that my name is XYZ. Then I will tell you, okay, you are XYZ, right? So this thing is known as reflexivity. If I know something in the LHS, definitely I know it. So it is known as reflexivity, like a mirror. So this is the first step. So whenever you are going to calculate any closure, the first step is use the law of reflexivity. So by this, what I can do, I have BC plus. So from BC, I can get B and C. D plus, so I will definitely get D over here. CF, I will definitely get CF from here. Done. Now, finding closure means you have to find out from this attribute how many attribute I can reach. Means if I know this attribute, how many attribute I can search. Now, start from the first point. So A to A, it is according to the reflexivity. Now, next part, how you can search. See, whenever you get something in the RHS, just see this RHS appears in the LHS or not. Yes, this thing appears in the LHS. Yes, this A is present here. Now, whatever component the A is pointing, just copy them here. Again, I am repeating. See, whatever you have in the RHS, just check whether this thing appears in the left hand side of the functional dependency or not. Yes, BC appears. So whatever BC is pointing out, just copy it. Again, you will try whatever you have in the RHS, check whether it appears in the LHS or not. If yes, whatever it is pointing, just copy it. Again, the same thing. Whatever you have in the RHS, that is C and F, check whether it is appearing in the LHS or not. Yes, whatever it is pointing, just copy it out over here. So here my point is, whatever component you are getting, it doesn't require that you have to take it accordingly, means you have to take it in order. No, you can consider AD also. AD is appearing or not. No, it is not present in the LHS, so I'm not considering it. So this is how you can find out the closure. So again, try it for the next version. So from BC, I am getting BC. So it is the first law, reflexive law. You have to apply it. Now, whatever you are getting in the RHS, check it appears in the LHS of the functional dependency or not. Yes. Then whatever you have, copy it over here, DE. Then again go for the thing. So here it is visible that D is appearing over here. So I can include this F section over here. So I'm just including it, this F. Then again I will check for C and F. Yes, CF is appearing. So copy this one, G over here. So this is the point you have to remember. So we keep on searching. So again we will try that somehow we can reach A or not. So BC I have tried, D I have tried, CF I have tried. So there is nothing left. So I will leave it. Now again D plus. So from D we will get D. Again the trick we will apply whether this D appears in the LHS or not. Yes. So we will include this F. Done. Then DF appears. No, only D is appear. Only F is not appearing. Or we have CF but we don't have C over here. So only D or only F or DF. It is not appearing in the LHS. So leave it. So again go for this CF. So from CF we will get CF, reflexive law. Now we will search for whether C is appearing or not. No. In the LHS we don't have only C. Only F is appearing or not? No. We don't have only F in the LHS, but we have CF altogether. So whatever your CF is pointing, just include it over here. That's it. The closure is done. So this is how you can find out the closure. So what you have to remember, the simple trick you have to remember. Whenever we are going to find closure, then you have to take only the LHS, that is A plus, BC plus, D plus and CF plus. And then whichever closure you are going to calculate, just apply the reflexive rule. From A we are getting A, from BC we are getting BC, from D we are getting D, and from CF we are getting CF. Simple. And then whatever component you are having, just go and check whether they are appearing in the LHS or not. That's it. So now here the main point. So why we are fighting for the closure. So if you know the closure, then it will be very clear to you which one is the key of my this table. Now you can ask me the question. Now can you tell me which one is the unique key or which one is the key that can identify your tuple uniquely? I can say yes. So here the rule is after finding the closure, if you find any situation where a particular attribute is pointing to all the attribute present in the relation. See, here A is pointing to A, B, C, D, E and F and G. All the attribute present in the relation means if I know the value of A, then I can search for all other attribute present in this table or in this relation. So here, what is the definition of the super key? The definition of the super key is after calculating the closure, if you find in the RHS all the attribute present in the relation, then this is known as super key. So for this relation, which one is your super key? A. Attribute A is the super key. So this is how you can identify. So what about B, C, D and CF? Definitely they are not super key because here A is absent. Here all other attributes except DF are absent. Here also the same thing. Not all the attributes are reachable from this values. So in this table we have only one super key, that is A. So now try to understand. Finding super key is very easy. So if I know the closure, then from this closure I can easily identify the super key. But now we have to fight for the candidate key. So finding candidate key is not so easy. So I will again tell you one trick by which you can define your candidate key easily. Now let's consider another relation. Say this one. Same table I am using. Say A, B, C, D, or I am just increasing the number of attributes. E, F, G, H. So it's a long table. We have so many attributes and some functional dependencies are given to you. So here today our challenge is to find out the appropriate candidate key, right? Now see, try to find out the trick. Now it's a very, very interesting thing. So this is your problem. So in your interview, it is asked that this is a table given. These are the number of attributes and these are the functional dependencies given to you. Now find out what is the candidate key. Tell me the definition of the candidate key. So now let's see. So whenever you are going to find out candidate key, the first trick is create one age graph. So now what is the meaning of age graph? Very simple. See the functional dependencies one by one. So it is written that if I know the value of AB, then I can search for C. So what I will do, I will write it like this. If I know the value of AB, then I can search for the value C. This is how your age graph will look like. Again, I am repeating. If I know the value of A, then I can search for DE. So if I know the value of A, then I can search for D, E. Then again, if I know the value of B, then I can search for F. If I know the value of B, then I can search for F. And again, if I know the value of F, then I can search for G and H. See, this is known as age graph. Why? See, AB to C is reachable. So here C is pointing by arrow. A to DE is reachable. So A to DE is reachable. So this is age graph. So now this is how you can draw the age graph. So this is the first step done. After this first step, do one thing. Find out which attributes is having incoming edge. Let's try to find out. So this attribute is having incoming edge, pointing. There is a pointer to C. So incoming edge, we have incoming edge to D and E. We have incoming edge to F. We have incoming edge to G. We have incoming edge to H. Now, which attributes do not have any incoming edge? It is clear. A and B is not having their incoming edge. Make a note. So here A and B is not having their incoming edge. Just copy them. So first what we are doing, we are creating the edge graph in this table by viewing this functional dependency. Then we are searching for the attributes which is having their incoming edge. If the attributes is having incoming edge, then we are not considering them. Why we are drawing this edge graph? Our target is to find out which is not having their incoming edge. So I have got it, AB. Now, there is a chance that whichever attributes is not having their incoming edge, probably they will be the candidate key. Now, you can ask me one question. How? Why you are claiming this? See, what is the meaning of functional dependency? If I have this value in my hand, then I can search for this value. Now, here AB is not having any incoming edge. Not having any incoming edge means towards AB means nobody, no other attribute can find this AB. AB can find C or AB can find other attributes too. But there is no one who can point to AB. So therefore here the conclusion is nobody can find AB as AB is not having any incoming edge. So this kind of attributes are known as essential attributes in DBMS. So there will be one question, what do you mean by essential attribute? According to this definition, the attributes, those are not having any incoming edge. In simple words, if no other attribute can find some attributes, so those are essential attributes. So we have identified this essential attributes. So once you have got the essential attribute, now you go for the step number 3. That is, find out the closure of the essential attributes. So now the latest trick of finding closure. First, without thinking anything, I will use the law of reflexivity. I will just copy from AB, I can find AB. It is simple thing. Now what we will see? We will see whether this attributes appears alone or together in the left hand side or not. Let's check. So AB appears together. Yes. So whatever AB is pointing, I will copy it here. Now only A is also there. Only A is also there in the left hand side. So I will copy whatever A is pointing. D, E. Now I will check. Again B. Yes. B is present in RHS and it is also appear in the LHS. Okay. So I will copy the thing that is B is pointing to F. Again I will check. See, we have F over here and this F is appearing in the LHS. So I will copy whatever we have in the RHS of F. So here try to understand, after finding the essential attribute, if I find out the closure, so this is the output of my closure. And what is the output? See, here the output is A, B, C, D, E, F, G, H. Means whatever attribute we have over here, the same number of attribute is present over here. So the definition is, if after finding any closure, if I get all the attributes of the relation R, then it is definitely known as super key. But here we are finding for candidate key. Since this AB is achieved after finding this edge graph, and it is proven to be an essential attribute, also this AB is considered as candidate key. So in the initial case, I have explained that if you find the candidate key, then it is very easy to conclude which one is your super key. So here my point is, whenever the question in your interview is asked that what do you mean by candidate key? So first point you have to tell them that the essential attributes in a particular relation R from which all other attributes are reachable are known as candidate key. And what is the definition of super key? From a attribute, if we get all other attributes in a relation, then it is a super key. So what is the difference between? See, whenever I'm defining candidate key, I'm stating that from an essential attribute, if I get all the attributes of a relation R, then it is a candidate key. However, from a attribute, essential, non-essential, I don't know. From a attribute, if I get all other attributes of a relation R, then it is a super key. So this is the first step that we have done. So this is the problem number 1. So this is a very simple case by which we can find out the candidate key. But we have more complexity. So we will just increase one level of complexity because this question is also very important. Now, consider case number 2. So there is a relation again, it is given. Again, some functional dependencies are also given. Again, the same question is asked, which one is your candidate key? So we will follow the step. So what is our first step? So we will draw the age graph. Age graph means we will look at this functional dependency and we will draw the age graph. So from BC, which attributes are reachable? ADE. So what I will do, from BC, which attributes are reachable? A, D and E. From D, which attribute is reachable? From D, B is reachable. So age graph is done. So now here my next question is what? Which attribute is not having an incoming edge? So it is simple. C is not having an incoming edge. Otherwise A, D, E, B, everyone is having an incoming edge. So C is the essential attribute proven. So at this point, what we can conclude? We can conclude that since C is an essential attribute, probably C may be a candidate key. I don't know. Now I have to check. So how can I check? I have to find out closure of C. So how to find out closure of C? Very simple. I will use the law of reflexivity. From C, I will get C. Now I will check whatever I am getting on the right hand side, whether they are appearing in the left hand side or not. So here we have C, but there exists no C in the left hand side. So try to understand. From here I cannot extract this. So only C is not there. So my point is, if I find out the closure of C, so what I am getting? Here I am getting that not all attributes are reachable. Here I am not getting all other attributes. So here my point is, try to understand. In the previous case, luckily, whichever essential attribute I have got, from that essential attribute, whenever I am finding closure, all the attributes were reachable. So AB was proven to be the candidate key. So this is your case number 2. Try to understand that here, whichever essential attribute we have got from this problem, after finding the closure of that particular attribute, we are not getting all the attributes present in the relation R in the RHS. So as a result, it is not a candidate key. So now here the trick number 2, please make a note. So here there is a confusion. If the question is asked, so whenever you are drawing any age graph, whichever essential attribute you are getting, is it mandatory that each and every time it will be a candidate key? Your answer will be no. Why? Because whenever we are pointing out the essential attribute, then we can say that probably it may be a candidate key. We have to check it. We have to prove it. How we can prove it? We have to prove it by using closure. After finding the closure, if we get all the attributes present in the relation, that is after writing the closure, if I get A, B, C, D and E, all the attributes of the relation, then only I can say it is a candidate key. So now in this case, we have failed. That is, our essential attribute C is not a candidate key. So what we will do in this situation? So how we could find out the candidate key? Because we know that in database management system, there should be one candidate key, right? There should be one key at least. So how we could find out the candidate key? So here try to understand a trick. See, we have proven that C is the essential attribute. So it is the must have attribute. So without C, I cannot proceed. So now the next step is what I will do. I will try to find out all combination of attribute with C. Means I will try to find out closure of AC. Means with the first attribute combined with C because C is essential. Now I will try out BC. With B, I will combine C. See, combining CC is not possible. CC means only one C. And only one C is not for use. So I'm omitting it. Then I will combine DC. And then I will combine EC. So this is how you can proceed. So whenever you fail to find out candidate key, but you know that this is your essential attribute. So this person is very important. So try to combine them with all other attributes and try to find out the closure. Now, how to find out the closure of AC? From AC, law of reflexivity, I will get definitely AC. Now I will check A or C appears in the LHS or not. No. Single A is not there, single C is not there, even AC is not there. So stop here. Now for BC. From BC, I will get BC. But now try to find out single B. No, it is not there, but BC is there. So from BC, whatever attributes BC is pointing out, I will copy each and every one. A, D and E. Now I will check. That is there any other thing? Yes, D is appearing in the LHS. D is pointing to B, but B is already included. So here I am not writing B. Writing 2B means it's a single B. So this is how we are getting. Now try to find out the closure of DC. From DC I am getting DC. Now try to find out D or C is appearing together or single. D is appearing. So from D we can get B. So I'm just writing B. Now we have CB. CB means BC, right? So CB means BC. So this is appearing. So ADE. Yes, I can include ADE in this case also. So now try to find out EC, closure of EC. So from EC we can find EC. Now check E and C together or alone appearing in the LHS or not. No. So stop it. So now astonishingly see from BC and from DC, we will be able to reach all the attributes A, B, C, D, E. A, B, C, D, E. From DC, we can also get A, B, C, D, E. So here my point is this table is having two candidate keys, DC and BC. These are the two candidate keys of this table. Also, this thing is also same. Writing CD or DC, writing BC or CB, all are same. So it doesn't mean that it has a 4 candidate key, right? So any of the order you have to write. So here, what is my conclusion? So there will be another question in your interview, that is, how many candidate key a particular table will have? See, the answer is more than one. It doesn't imply that a table should have always one candidate key. I may have 2, 3, 4, 5, 6 candidate key. It depends on the situation. So here try to understand this case is very, very important. So whenever after finding the closure you are not be able to reach all the attributes, then the only trick is combine this essential attribute with all other attributes and then try to find out the closure. And you will definitely get the candidate key. But here there is a next definition. A table may have more than one candidate key. But there is another question, that is, can we try for this combination ACE by taking 3 attributes together? So here my point is there is one definition of the candidate keys. Okay, I will just tell you what is happening here. Say, try to find out the closure of ACE. I can take any number of attributes. C is there as an essential attribute. So from ACE, I can get ACE. But here, from this, see, try to understand whether they are appearing in the LHS or not. No, they are not appearing. So from AC, I am getting AC. So it is not contributing anything. Then you can also try for B, C, D. From BCD, I am getting BCD. Now try BC is appearing. So from this, I am getting ADE. So here from BCD, all other attributes are reachable. Now you can tell me one thing. Okay, so at this point of time, you can say that BCD is another candidate key. Yes, because from BCD it is also reachable. Also, I can try for CDE. Yes, I can try for this. So now I will tell you, okay, try for four attribute B, C, D like this. So is there any solution for that? Yes, there is one solution. So there is a concept of minimality. So what do you mean by minimality? See, BCD is a candidate key. According to us, say from BCD, all other attributes are reachable. So now you can ask me one question, is it a candidate key? Then I will tell you no. Then you will definitely ask me why it is not a candidate key, because it is satisfying all of the property. See, here is the difference. If you find any situation like this where subset of this key CD itself is a candidate key, then it is not a minimal set. See, from BCD, if you take only CD, then it is a candidate key, right? So in this case, try to understand if you find any situation where from LHS you can get all the attributes of the relation, then you just check once that is there exist any subset that alone can identify all the attributes. So if yes, then it is not a minimal thing. If it is not a minimal thing, then it is not a candidate key. So in this case, BCD fails since CD is a candidate key. So in this case, definitely we have two candidate key. So now you can ask me one question. So what happened with BCD? So what we can call, because from BCD, all attributes are reachable? Yes. In this case, we can call BCD as super key. And definition of the super key means from which all other attributes are reachable. And what is the definition of candidate key? See, if we have any LHS from which all the attributes are reachable, at this point of time it is super key, but now try to find out whether any particular subset is finding all attributes alone or not. If yes, then it is not a minimal. So we are always opt for minimality. So here that's why in the book it is written that minimal subset of super key is known as candidate key. So in this case, BCD is a super key and minimal subset CD of this key is known as candidate key. So CD is the candidate key, but BCD is the super key. So this is the definition.